Hey everyone, today we'll be looking at longest increasing path in a matrix. We'll try to solve it in less than 15 minutes. Okay, it's a hard problem, so hopefully we can solve it. But if not, then Leetcode Baba Zindabad. Let's do this. Okay, given an m into n integer matrix, return the length of the longest increasing path in a matrix. From each cell, you can either move in four directions: left, right, up, down. You may not diagonally move or move outside the boundary. That is, wraparound is not allowed. Okay, so yeah, the longest increasing path is 1269. Mm-hmm. Okay. Uh, 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 um, mhm. The longest increasing path is, so why not 11269? That is, wraparound is not allowed. 3, 4, 5, 6. In here, 1, 2. I don't get it. For each cell, you can either move. Okay, you may not move diagonally or move outside the boundary. That is, wraparound is not allowed. Yeah, I know. I get it. But duplicates longest increasing path, right? Longest increasing path in matrix. So for me, if I look at this 1269, and I guess the number should not get repeated. That is one of the challenge that is there. Got it. So looking at the solution, looking at the example, the number shouldn't get repeated. If it gets repeated, then yeah. So that makes things easier. um, if we look at that way. So if I start at I have to traverse through um, the array, and let's say if I traverse through 9 first, or how should I decide which should be my moving point, or how should we decide it? I think we have to traverse through the entire array, entire matrix, and for every cell, we need to calculate the distance. And if the new cell, if we traverse the cell and if it is the longest one, then we need to replace the array with a new one. But other than that, I don't think so. We need to do anything other than that. So, okay. First of all, we need to see if it is in increasing order, and if it is not equal to less than or equal to the previous cell that we visited. So we want to make sure that it doesn't happen that way, and we do not revisit the cell that we have already visited. So that we need to take care of. So that being said, okay, so what we need to do is every time we traverse any cell, I believe we need to have an array which in which we'll store the number of nodes that we have traversed in an increasing order. So yeah, that's what we should be returning at the end. Yeah. So how can we do that? How can we do it? Mhm. So let's do this. We know for matter of fact that we need to traverse the entire length of the matrix, right? Is equal to before doing that, let's take in row is equal to row length is equal to matrix dot length. Let call len is equal to matrix of 0 dot length. So we got those two, and what we need to do is we need to traverse the row len I plus plus, and for let j is equal to 0, j is less than column len j plus plus. I need to traverse these. Okay, yeah. And one more thing that we need to make sure is that let result is equal to an empty array, right? If so, we'll call let new result, which will be returned by TFS of I and j, that will be sending along with the visited. Okay, so along with the visited, and here we'll check if new result dot length is greater than result dot length. If it is, then we will update result is equal to new result. Okay, yeah, that's what we'll do. And yeah, once we have done that, we also need to make sure that we return our result in the end. Yeah, so that's that. Um, and finally, what we need to do is that we need to start sending an empty array. And one more thing, we need to create visited array. Visited is equal to new array. You need to pass the row len to it, and then we need to also mm, fill it and map map over it, and need to return array colon dot fill with false, and that should exactly give us a 2D matrix that will be initially false. Okay, so we are here, and what we are going to do here is function. We need to define RDFS function, right? That's where the magic will happen. We accept R and C, then we accept the visited. What we also need to send is, along before the visited, we also need to send the matrix that is given to us, right? So once we have the matrix access matrix, and also we need to result, let's call it result. Okay, yeah. once we have this, we need to check if we are not going out of bound. And yeah, we are not going out of bound, and we need to also check with the previous value. If it is not equal to the previous value, we need to also check that, right? Mm-hmm. So let's do the basic check first. If r is less than 0, or if r is greater than equal to matrix dot length, or or else for simplicity's sake, we just define it here so that yeah, we can have access to the row len and call len. Row, let's write it properly. Row len, and c is, sorry, my bad. C is less than 0, or c is greater than equal to call len. Yeah, if any of these things happen, we need to go back, and instead of, okay, or visited of r and c equals to true, equals to true, then also we need to return, right? Return back. We don't want to do anything here. So return, and just in case, if so I come here 9, it's visited, I come here, so what I need to do is I also need to send back if it is equal to the previous one, right? Previous, right? So how can we do that? I can have it here, uh, define the previous one, pre, or define null here, and here I can just say previous, and I don't need this matrix anymore. I also don't need the visited anymore, because we are anyways writing it in the the function itself. So I have this previous value and the result value. Okay, I need these. Let's call it res instead of result. Okay, and if prev is not equal to null, and prev is not equal to null, and matrix of current r and c current value is equal to previous, then we don't do anything, we return. We don't want part of this, so we return, right? We don't want to do any of this. And if everything goes well, we come here. What we do is we have to first set visited of that R and C equals to true. And what we also need to do is, yeah, and we also need to make sure, yeah, instead of equal to prev, we need to make sure that if it is less than equal to previous, then there is no increasing order, right? So we return. So if it is increasing, then we know for sure that, okay, and we need to also put matrix of I and j here. Okay, so I and j here, and we need to push res dot push matrix of R and C, or what we can do is we can simply, so oh my goodness, my laptop is running slow, sorry about that. Let um, let current is equal to, we'll put this in here, let get rid of this and let call it current. Okay, so we push the current value into onto the matrix, onto the result array, and what we need to do is top left, right, bottom right. We need to go there. So DFS R plus 1, R minus 1 is top, C, then previous is now our current, and result is result. I need to figure out how I'll be returning my array to, so this would be plus 1, this would be nothing, this would be minus, oh, sorry, minus 1, and this would be plus 1. And at the, before leaving this, we need to make sure that visited of R and C, uh, we are making it to false. Okay, so at the end, I suppose we can just return the result, return the res, and that's how we'll get our new value. So what say guys, will that work? Only way to find out is running this function. Okay, it did not work, but let's check. What did it send? Nan. It sent out nan. Why is that? Why did you send out nan? Do you have a good reason for that? DFS, IG matrix. If previous is not equal to null, and then matrix, yeah, this will, for the first case, it won't be triggered, but for the rest of the cases, it will be triggered. So, yeah, let me check if what console.log, if in fact we are getting anything back from the DFS function, or at least like what are we getting exactly. So what happened here was 9999. So I came in here, I saw this guy. Okay, so yeah, so let's say I came in here, I went 9 as I've already added. Oh yeah, I added the 9 again. I added the 9 again. I shouldn't have done that. If prev is, I guess to deal with this, we can just send a empty thing, and it should take care of this instead of, unnecessarily um, doing it here. So there should be just one 9 now. So 9 comes in, 9, we send 9, and then this was less, then this was less, then it sent this one, then 4, 9, 4, 8. How can it send 4, 8, 9? Really? Current, it shouldn't have sent 4, 8, 9. It should have just sent 4, 8, or 4, 9. Guys, I'm going on a break. I'll be back soon. Okay. Hey everyone. So we are back. Hello, hello. Okay, we are connected, but why is this not showing anything? Anyways, okay. So I won't worry about that. But yeah, let's see if okay. So 489. I came to 4, then I went. Okay, that is a problem, right? I went to a 9 and I went to 8. It should be an increasing path, right? Uh, mm, mm, mm. So every path that we take could lead to a maximum path. Okay, that's what I understand. And what we cannot have is, okay, what we cannot have is, so see, if we send it to 9 and 8, at this time 4 and 9 would be the one. And okay, what the hell, man? Every time. So let's go back to the exact. Let me first of all get rid of everything that is over here. Okay. Okay. So I have this guy 994866211. Okay, I drew this out. So let's go here. And so what I'm currently doing is if I go to 4, then I can move this direction, this direction, this direction, this direction. These two, these two directions, these two directions are not of any use, right? Because it will return out. So what we are interested in is these two values. Uh, then, then what we can do is that what we can do is we can we can so let's see when we traverse the 8, what do we do with the array? So when we traverse the array, we have 4 in it, then 8 is greater, then we add 8 to it, right? Okay, and that's what we do. Then 8, coming to 8, we can go here, here. So everything is less than that, then we end up returning a result. a result back. So we have 4 and 8. 8 returned back. So this guy goes here, 4 and 9. So at this point of time, I believe the result is 4, 8. Okay, we are sending the same result to this guy, right? So that's why it is behaving that way. It is behaving that way. Yeah. So instead of instead of instead of sending everything like this, result is having the same reference, right? So instead of sending this way, what we can do is, what if we do this? We spread this out. But anyways, like let's keep it. So let's say this guy returns something, this guy returns something, this guy returns something. To send the longest of these three. So I'll just do it for more couple of more minutes. Oh, let top is equal to DFS. Let uh, bottom is equal to DFS. Let left is equal to DFS. Let right is equal to DFS. So yeah, we know that we want it. We want this. So whatever is returned back, so this returns nothing, returns an empty array, and this returns an empty array, return an empty array. So this guy, so once, okay, so let's go back to here. So this guy will return an empty array, this guy return an empty array, this guy 8, then it goes here, it goes here, this returns an empty array to this guy. This guy, if it sends res, I guess what we should be doing is we should be checking whose length is greater and send that finally. So out of these four, whose length is greater, we need to send that back. So how should we find out whose length is greater? Like top dot length is equal to, if it is greater than equal to, if it is greater than bottom, or let's say equal to, let's say greater than equal to bottom, then top is equal to, and sorry, bottom, let um, greater array is equal to like this, and let, let's call it db array, and lr array is equal to top left dot length is greater than equal to right dot length, then left or right, and finally what we need, and finally we need to check, let max array is equal to db array dot length is greater than equal to lr array dot length question db array or lr array, and finally we need to send max array. Is that okay? Yeah, I guess so. And if we run this now, we shouldn't get 48. OMG. Okay, so std out. So let's see console log, what console log prints. Top dollar top bottom dollar bottom, then left, then right, right, bottom. Oh, sorry, left. Okay, so I guess let's check it now. So we are sending 9, top, bottom, left, right, returns nothing because, yeah. So sending 9 again, nothing, returns nothing. So top, bottom, left, right, returns nothing. So bottom returns 4, 8, and left returns 4, 8, 9. So meaning of this is that res, how can we send just a value like this is res, right? This is res. I want to send it 4, 8. I don't want to send it anything other than that. Like if I send this res, it okay. So how can we do that res? Like I'm thinking, हेलो। एक मिनट। हाँ, बोलो। Okay, guys, after banging my head for several hours on this, we don't have that much of time. Um, so yeah, I guess we can see how this guy solved it.
Welcome back, and let's write some more Leetcode today. So today let's solve the problem longest increasing path in a matrix. And while this is a hard problem, I would definitely say it's one of the more doable hard problems. There's nothing crazy involved, but it is somewhat difficult. We're given an m by n matrix that is filled with integers, and the integers are going to be, I believe, 0 or greater than 0, so mostly positive integers. And we want to return the length of the longest increasing path in this matrix. And we are allowed to move only in 4 directions, left, right, up, or down. We're not allowed to move diagonally. And of course, we can't go outside of the boundaries. So let's just start with some observations. First of all, this is an example, and you can see that this is the path that is the longest. It's of length 4, and it's in increasing order. Obviously, we can start with pretty much any value, right? And pretty much starting at any position, we can create a path of at least length 1, right? This is a path of length 1. This is a path of length 1. But, starting from here, then the next position that we go to is a 2. It has to be greater than 1, which it is, and then the next one is 6. That's greater, and then 9, that's also greater. But from here, we can't really go anywhere else. Right? We're allowed to move here, but this one is not greater than 9. It's just exactly 9, so that's the longest path. Now, one thing you might be wondering is, can we, reuse the same value multiple times, right? What if we have a loop of some kind? Well, just think about it for a second. If this is an increasing path, of course we can't reuse any values because take a look at our path, right? The value that we get to is going to be greater than all the previous values anyway. So how could we possibly reuse any of the values in our path? We're not allowed to. Now, they don't state that in the problem statement, but that's an observation that you have to make on your own. And in this case, that's true. And another observation we can make without even trying to understand, what's the algorithm we'd use for this problem, just by looking at this example, we can make a very important observation, and that is that if this is the longest increasing path and it's of length 4, that means the longest increasing path starting at this position is going to be of length 4. But what about the longest increasing path starting at this position over here? What is it going to be? In this case, we can see that there is a path right now starting from it that's increasing, that's of length.
Did we get a path, increasing path from 268? Okay, so we did send one, the top, bottom, left, right. Why was it? 6, 9. How come 6, 9 and why not 1? So yeah, I did messed up something. But yeah, let's do this.
Length are going to be larger than 3? Of course not, because if there were, wouldn't here it's 1, because remember the solution to this problem, and then I bet it will make sense. Now let's think about this. What's the most basic brute force way that we could find the longest increasing path? Well, we could basically start at every single position and say maybe the longest increasing path will start here, maybe it'll start here, maybe it'll start here, right? Who knows? They don't tell us where we have to start, so we pretty much have to try every single position. That's the brute force. And let's say we, record that in a grid that's the same size as the grid we have here. I'm going to call it LIP for longest increasing path. And once we do that, once we filled up every value in here, we can just take the maximum of them and then return that. That'll be the length of the longest increasing path. Okay, so for any particular position, how do we find the longest length? Well, the brute force, again, is just going to be a simple DFS. I hope you're familiar with the DFS algorithm. It's a pretty standard graph algorithm, and you definitely will need it for hard level problems. We're going to run a DFS starting from this position, going in 4 directions, right? Up, down, left, right. Of course, if we go out of bounds to the top or to the left or any other direction, we're not going to continue there, of course. Okay, so we can't go out of bounds. Let's try going right, starting from here. Are we allowed to go here? Well, we have to compare the
No.
values, right? We have to look at this value. Is it greater than the previous value? It's not greater than the previous value, so we can't go here, right? We're not allowed to go there starting from here. Okay, let's try going down. That's the only position left that we have. It's a 6. That's also not greater than 9, so we can't go there either. So we're pretty much not allowed to go anywhere. So what's the length from here? It's 1, because remember, 1 is basically like the default value. We can always have a length of 1 starting at any position. Okay, so we did that. Now let's go to the next position. Similarly, we're not allowed to go in any of the 4 directions because none of them have a greater value, so we'll also put a 1 here. Okay, now let's try the 4, and this is where things are going to get interesting, so pay attention. We can't go up, we can't go to the right, but we can go to the left. And finally, we see a value that's greater than the original. 9 is greater than 4, so we are allowed to go here. That's awesome. But now we're doing DFS. Does that mean recursively we're going to run DFS on this position again? Well, we don't have to, because we already ran DFS on this position and we already found the longest increasing path starting from that position. The length of it is 1. So we don't have to repeat that work because we stored the repeated work inside of this matrix. So we know that starting from 4, we can go to this 9, and that's a path of length 2. That's at least one path that we can create. Okay, we do have one more direction to try though. We can, from 4, we can go down to the 8. We haven't ran DFS on this position yet, so we're going to have to do that now. DFS. Okay, let's go to the right. That's out of bounds. Okay, let's go up. Should we even go up? Well, in reality, we shouldn't, but if our algorithm is programmed to try going up, it'll still work for us because, of course, we came from the 4, so we know that the value up above is less than 8. So if we try going up, it's not going to work anyway, so it's okay to leave that in the code because it's not going to break anything. So that's good for us because it keeps our DFS pretty simple. Okay, now let's try going down. We can't go down because 1 is less than 8. We want it to be greater than 8. Let's try going to the left. Okay, 6 is also less than 8. We want it to be greater than 8. Okay, so we couldn't go anywhere, but we'd still, of the 2 paths, both of them were the same length, so we can put a 2 here. Starting from this position, the longest increasing path is length 2. But did we do anything else? Well, we started at the 8 and we ran DFS from this position. So not only did we determine that the LIP from here is 2, but we also determined that the LIP from 8 is 1 because we couldn't go anywhere starting from 8. Are you starting to see how this algorithm itself, even the DFS brute force, is not inefficient because we're caching the work. We're storing the work in a matrix. So this isn't even a brute force solution as long as you implement it correctly. It's actually very efficient as long as we don't repeat the work. So now when we're not quite at the 8 yet, right? Because we're going in order in our matrix. But once we get to the 8, we'll know we already ran DFS on it and we won't have to repeat that work. So now that you're probably starting to get the idea, I'm going to start fast forwarding through this explanation. So now let's run DFS starting from the 6. We try going left, can't. We try going right, we can't. We try going down, we also can't do that. We try going up, okay, we can do that, and we know that we already computed the LIP from here. It's 1, so we can say the LIP from starting at 6 is going to be 2. Now let's go to the second 6. We can't go left, it's less than 6. We can't go down, it's also that this will be a path of length 2. We know, 1 from here, so that's 1 possible. We have a tie position, computed it, so we don't repeat up over here. It's length the 2 value, that's which will be 1 plus. We can't go down, greater than 1 plus 2, 4 plus 1, so we're going to put a return 4. We don't actually have to return a solution, and it's pretty efficient, but how do we know it's efficient? What's the time complexity? Of course, the memory complexity is big O n times m. Those are the dimensions of the matrix because we're using extra space here, but what's the time complexity? It's also big O of n times m. Just think about the intuition behind it. Let's say our matrix was in such a way that when we ran DFS at the first position, we, had a path such like this, and then we went here, and then we went there, then here, then here, then here. Basically, we visit the entire matrix in one DFS. That's going to take big O of n times m to run that DFS. But the good thing about that is going to be after we've done that, we're going to have computed every LIP from every single position, right? And then when we visit the remaining values of the matrix, each of those is going to be computed in big O of 1 time. So, having done the repeated work at the beginning wasn't such a big deal because the remainder is going to be very easy. Or value, right? Let's say each of them was exactly 2, but we'd see that we can't go in any of the 4 directions. So for each of these, in that case as well, the time complexity would be big O of 1, which means why this is an efficient solution. And with that being said, let's finally jump into the code. Dimensional graph problems, matrix problems in a very formulaic way, and I've done it, put it in some. We're going to need to know those dimensions. In this case, we're going to have a hash map because it's pretty easy to do that in Python. We're basically going to be using path. Now, of course, you could just use a 2-dimensional matrix if you're doing this in Java or whatever if you want. And maybe I honestly should do that as well, but I'm really used to doing it this way because you can kind of just turn your brain off. And next, we're going to use DFS. We have a function inside of a function, so we don't have to pass in every variable, such as these 3 that I defined up above, but we are going to pass in the position that we're currently visiting, which is order. So we are going to pass in what the previous value ends up being. And then with all, graph traversals, the first thing you want to check is, did we go out of bounds? Is the row less than 0, or is the row exactly equal to the number of rows, which means it's too big? Or same exact thing with the column. Is column less than 0, or is column equal to the number of columns? Because that means it's too big. And the last condition in this case is going to be, is the path not increasing? How do we know that? Well, the value that we're currently visiting, which is the matrix at the row column position, is less than or equal to the previous value. That means it's not increasing. And if it's not increasing, then we are just going to return. We can return 0 just to say that the increasing path was just 0. Okay, so that's one base case. And the second base case is a little bit easier. That's if we already computed the LIP at this position, RC, and we know that because if this is in our DP hash map as a key value, then we can return whatever the length of it was that we computed and ended up storing in our DP cache. So there we go. Okay, now to actually compute the length, we're just going to call it result and initially set it to 1 because we know it's at least going to be 1. That's the minimum it could possibly be. And now we could use a loop to go through all four of the directions, but I don't think it's really necessary. We can just kind of copy and paste the same line like 4 times. I prefer doing that rather than doing a loop, but you can do what you prefer. So one, we know we're going to run DFS, right? We're going to run DFS on one of the neighboring positions. One of them could be R plus 1, and then the column is the same. And what is going to be the previous value that we pass in? Of course, it's going to be the current value right now. So row, column. And we only want to update the result if this is greater than the result. So what we want to do is set this equal, or actually, this alone is not going to be the length, because this is going to tell us the longest increasing path starting at row plus 1. And if that's the case, what we actually want the length to be is from this position that we're currently at. So we're going to take this and add 1 to it, 1 plus that. Similar to how I was doing it, or I was talking about it in the drawing explanation. Okay, so once we have that, then we want to take the max of the current maximum result, maximum length, and take this, update the result if this is greater than the result. So what we want to do is set this equal, or actually, this alone is not going to be the length, because this is going to tell us the longest increasing path starting at row plus 1. And if that's the case, what we actually want the length to be is from this position that we're currently at. So we're going to take this and add 1 to it, 1 plus that. Similar to how I was doing it, or I was talking about it in the drawing explanation. Okay, so once we have that, then we want to take the max of the current maximum result, maximum length, and the max of this, and then update it accordingly. And this is where we copy and paste 4 times, because we want to go in all four of the directions. So R plus 1, R minus 1, also column plus 1 and column minus 1. Okay, and when we're done with that, the last thing we have to do is, now that we've actually computed the LIP starting at this position, we want to make sure to actually throw it into our DP cache. So let's do that before we end up returning. So let's store that. And then once we've stored it, we can go ahead and return it. So then the next time, if we ever call DFS starting from the same position, we'll end up returning it from our cache rather than redoing the DFS. So that's where we're saving our time. Now that we've defined our DFS, all that's left is to actually call it. And remember, we want to run DFS starting from pretty much every single position in the grid. So we can do a nested for loop to do that. So go through every row, go through every single column. When we do that, we also want to run DFS on every coordinate. And what's the previous value that we're going to pass in for that? Well, we know that every value in the matrix is going to be 0 or greater than 0. So a default value we can pass in for the previous value is -1, because we never want this to return if we're looking at like the first value, right? And so if we pass in -1, this
Oh, I thought we have to return an array. Okay, okay, got it, got it.
comparison will never evaluate to true, right? None of these values is ever going to be less than -1. That's good. So that's why we're doing it like this. So once we've done that, we're good to go. The last thing we have to do is just return whatever the maximum was. So we can just take our DP values, which will return a list of all the values, and just take the maximum of that. Now, we probably don't need to do it like this. Like, we could have just maintained another variable over here, and maybe have just called it LIP, longest increasing path, and then just continuously updated it based on the maximum that was returned. You can do it however you want. The time complexity is the same, even though we're iterating over the entire matrix again pretty much by doing this. That's the idea. Let's just run this to make sure that it works. And as you can see on the left, yes, it does work, and it's about as efficient as you can get for this problem. So I really hope that this was helpful. If it was, please like and subscribe. It really supports the channel.
Okay, so yeah, let's try to solve this problem on our own, and let's see. how it goes. Okay, guys.